one from a theoretical part, and one more is the problematic. Okay, so let's start some of the definitions. Here is a one thing which I would like to focus is it's a memory management. So no need to think about a processor, how processes will work. Just we should remember how the students will get a seat in the examination, okay, or how they will get how they can sit, how they can be made sit in the classes, like that small idea, virtual. Okay, so now let's start with some of the basic. If we want to execute a program, it is compulsory that what we have studied is we should store a program in a hard disk, then program should be taken onto the RAM and execution. So this is simple explanation. From the hard disk, you take up a program, load onto RAM and execute. This is possible when we have a simple lab programs, some standard algorithms like DA algorithms or ARM subject lab experiment. But if we execute some of the programs or projects like environment, I mean weather report calculation, okay, and nuclear reaction output or a programs, in such a situation we cannot definitely say a program will be completely entire program may be loaded on the RAM. May be possible, may not be possible. Okay, so that means what? To execute a program, it is compulsory to bring it from hard disk on the RAM is compulsory. But is it compulsory to bring complete program on the RAM and execute? That is what we are studying in this chapter. I hope you understood. Okay, so meaning is we cannot make a big or a complex and a lengthy program from hard disk on the RAM to execute some part of it. Okay, sometimes small part of a program is loaded. Okay, let me try to give one real world example. I want to withdraw the money from a ATM. Okay, so what are the options I have in the ATM services? First, balance check. Second one, cash withdrawal. Third one, pin generation, pin change, transfer. These all are the 5 options. But what I want is I want a withdrawal. So whenever I insert a card, okay, I insert a card and pin number verified. Then second step is withdrawal of a cash. When we are withdrawing a cash, it doesn't mean we should have all the facilities loaded on the RAM, because I have selected one option among the 5. That means only that option should be executed. If I have selected cash withdrawal, the other subroutines called mini statement printing, then pin change, pin generation, etc. should not work. Okay, I hope you can easily see. One more thing. Okay, so assume that you have 6 notebooks in your bag during the class hours. Okay, 6 notebooks for a 6 different subject. If a subject 1 starts, are you going to store the data on the board in all the 6 subjects notebook or only one? So we are going to take the notebook correspond to that subject. We will write data only in that notebook. So meaning is what? Even though we have all our 6 notebooks ready, but if one subject class is going on, we used to interact with only one notebook. Okay, in the same way, it is not needed to load all program, load only related part of the program. That is called as selective loading. This is a smartness, selective loading. What kind of data we can load? We can load error code. Not only the best cases I am listing. Best cases are what? Instructions. Some of the plus instruction, minus, logical and, or, etc. Along with the normal execution, some special error codes, unusual routines, large data structures. These all also we can load them, but selectively. Okay, error code. It is not required if program is correct. Correct. If program is correct, we don't need help of error code. Okay. When we need help of error code is when program is not possible to execute. See here, we will visit a ATM. We will try to withdraw the money, 5,000 from my account. I have sufficient amount, but thing is, ATM doesn't have that much amount, that machine. Okay, so it will give insufficient funds available in this machine, not in the account. Account has a sufficient, but ATM is. So it will also attach one statement, please visit nearby ATM center, like that it will give. So that is called as error code. When it will come, when process is not possible to execute successfully. So similarly, not all the time part of a program, sorry, all parts of the programs are not loaded. It depends upon the situation. So what happens if we load entire program? The RAM will be unused most of the parts. See, 5 options are there in the ATM. Among one, every user will do only one. Okay, only one. Anyone among 5, one he will do at any time. Okay, so when he opted one activity, why to load other activities? Just we have to unload them from the memory so that process becomes faster. Okay, I hope it is clear now. So now coming for this point, so the such a part of a program which is loaded is called as partially loaded program. Partially loaded program. Now the condition why we need this partially loaded program and when we need this partially loaded program concept. So first thing, if we are working in same computer resource among multiple users or multiple programs, multi-programming or multi-users, that time every person want to give his own data, he want to process his own data. That time process the resources are shared among the multiple users. If we give complete allocation for first user, he may load important as well as unnecessary unnecessary data onto the RAM. Okay, so what is the problem with that is, so second person, even though he want to execute little part which is important for him right now, he may not load the data. So that problem will come. So to avoid that, it is important that instead of loading full program, we can load the partial program which is very essential and about to execute, then continue the execution. And also, as I mentioned, so instead of loading full program, if you load part of the program which is very essential right now, okay, so definitely total workload on the RAM reduces. We can expect faster and also more throughput. Why throughput? At right now, first person using partial, second person also uses a partial, third program will also uses a partial, means at a time we can use execute 3 programs. So definitely it makes number of execution per unit time more and utilization also more, because you are giving only required work. Okay, but what is important that you are giving unnecessary work, unnecessary space you are not utilizing. So that definitely that increases performance and throughput. Okay, now what do you mean by virtual memory? It is here I will show the first diagram. I hope you can see now. The left side of our screen is I mean my side is the virtual memory. Here it's a physical memory. As we have seen in we have discussed in the previous chapter, page table and all. For every page in the virtual memory, there will be a corresponding frame. Okay, and the every content of this is, I mean, this virtual memory will be there in the physical memory, and both are mapped using memory map technique called page table. Okay, really speaking, how the virtual physical memory will be, it is a 3-dimensional space where each consisting of frames. Okay, so this is a disk. Okay, so virtual space means it's a separated from separation of a logical memory with the physical memory. Okay, and as I told, only the selected part of the program is loaded on virtual memory, not the all. Say for example, what we can tell you is, if you want to watch some games or play some online game, okay, so what happens? You are going to select some of the race type of game. Okay, so in the total software there may be 25 tracks, okay, to play the race, but one which you select only that is loaded, remaining 24 track and their architecture are removed. So if all 25 tracks are loaded on your this one mobile, definitely mobile will become slow. So to avoid that, we have the concept of virtual memory. So what we feel now, once that the track what we have selected is visible on my mobile and remaining 24 are not visible. So my question is where those 24 tracks are stored, that is itself is called as virtual memory. So can we access virtual memory? Yes. That means can we change the track of selection where I want to play the race type of game? Yes, of course. So suddenly what happens? Whatever is presently really I have selected track, that is copied onto physical memory of my mobile. So that is removed out. What I am going to select in the next step, that is that is present in virtual memory, that is loaded back onto physical memory of my mobile, and I can play in the new track. So can I change the car appearance or bike appearance? Yes. So present appearances are in a physical memory, they are removed out. New appearances from virtual memory, they are copied into physical memory. So this is how the transfer of data between virtual memory and physical memory. What we feel that I have in my mobile only selected track is there, only the architecture or a pattern of what I have decided for my car, my bike is there in my mobile. But really speaking, all features, all tracks are there in a virtual memory. But since we have derived small part of the virtual memory on my mobile, so I can see the selected part of it. Okay, whichever we have selected, that is there in the physical memory. Okay, now will there be another person in the race? Yes, definitely. That's why we can say it's a shared by multiple process. If we are competing among 8 people or two person, two participant, definitely same track is shared. Okay, so that's what. Hence now we can say what, two car race, 4 cars race, 10 cars race. See the every car is controlled by one process, like how we are controlling our car or our bike in the race. Same way every car has their separate controlling process. So we can say now all processes are running concurrently or parallelly. So every process will need their separate input and output. Okay, not all the time. If I am playing in online game, so whatever I give input, I mean signal of acceleration, slow down of a vehicle, right move, taking, left taking, those are corresponds to my vehicle. Same way another person, he's control to his vehicle. Okay, I think every IO will be there for every separate process. Okay, now we have studied virtual address space. It's a collection of virtual address starting from 0 to the highest. I can show you here. Virtual memory, it's a virtual address space starting from 0 to the highest value. Okay. So now what we can say, as I mentioned, generally it starts from 0, it will go for the highest, continuously available. So I hope you can see in our previous 0, 1, 2, 3, 4 like that. Okay. And physical memory, physical memory made up of frames, whereas logical memory made up of, here let me draw, this is a logical address space or a virtual address space, logical address space, and this is what physical address space. Okay, physical address space. So logical address space is made up of pages, whereas a physical address space is made up of frames. Okay, so like how the logical address is controlled by continuous pages, same way physical address space is monitored by continuously allocated frames. Okay, now the question. So now only we are working on left part of here this virtual memory. There we are working in this chapter. Okay, studying more about how the virtual address is, how it corresponds to the physical address. Like that we are studying. Now, so who is responsible for one logical address corresponding to one physical address is memory management unit. Okay, memory management unit. So now simple way, some class is started, some subject class is started, you have 6 notebooks. Okay, so who has started and which book, both are not at all related. Who has to make a decision which class, which notebook we have to write, that is decided by the student. So like this it is called as memory management unit. Okay, so fine. Next is virtual memory can be how we can implement a virtual memory, that will explain. Okay, so there are two methods. One is a demand paging and demand segmentation. Okay, so here are the concepts. Okay, fine. Okay, before going to those 2 points, let me explain once this one. All virtual memory is divided into pages. There will be one page table which will map pages onto frames. All the spaces of physical memory is divided into frames. Okay, for every virtual every page there will be one corresponding frames. Okay, I hope you remember shared processes slide. So what happened, there was a concept called AD1 among multiple processes, but it is in a only one frame. Because of that reason, virtual memory will be generally looks more than the physical memory. What happens here, we need to show ED1 3 times. If you want, you can refer the previous chapter last session slide. ED1 in all the 3 processes we have shown, but in the frame we have shown it only once. That is also compulsory. We cannot show multiple times ED1. There will be only one frame. Correct. Okay. We feel that virtual memory is more size than the physical. Okay, because every process will feel like that, because virtual memory is given for user. What we feel, as I mentioned, the track is for me, and the car is I mean my car is has a facility. Same way other person can also use the same track, same type of facilities in the car, same concept. Okay, really speaking, they are one time but used by many a time. See, if 8 participants are there and there are 25 tracks, all 8 participant has chosen track number 2. See, this is one track. So 8 participants are mapped and they are taking that competition. Okay, I hope you understood difference between virtual and the physical memory. Okay, now coming back to the second point after this background, demand paging and copywriting. Okay, so what do you mean by demand paging? That is with the help of virtual address space. So very simple word, demand a page. That means whatever is not present, for that we have to request. Okay, so if I definitely I will not put up any demand or any request. I will put a request or I will go for a demand only for which I don't have. So now the question, how the demand is done, on what basis demand is fulfilled or request is what supplied. Okay, whatever is supplied. For that, we should understand more about a virtual space. So before I could take up this one point, for every process, there will be something like space reserved. So how the space is off for every process, I will show you. So for every process, there will be a stack, there will be a heap, there will be a data, there will be a code. So instead of process, if you assume program, not a ROM, you can think. So if I create one program as a user one, I will get this much area. So like that, user one space, I'm executing this program. User two, my project mate, he's also executing this area. So what happened here? We look like we thought that our space is started from 0. We have got this much area. Correct. So what we feel? Okay, memory is given only for me. That is what our virtual feeling. Really speaking, what happens? Like this, if 3 person are working on same resource, same computer, okay, see now how it allocates like this continuously. First user, he feels this much. I mean, he's a resource. Second user resource, third user resource. But do all processes starting address is 0? You can see here. If these are continuously allocated, there cannot be 0 space for every time. Okay, so now what happens is, here I will show this important. See this. If I assume upward arrow mark, okay, see this. This is per first area is for program 1 by user 1. Second area is for program 2, which is executing by user 2. Program 3, user 3. So what user 3 feel? He has a full memory access. User 2 feels the same. User 1 feels the same. But really speaking, the memory is like this. See this: 0, then 10, then 20, then 30. So now what is a zeroth for the corresponding you is 21st. Okay. So user 3 feels he has got a full memory, but really speaking, how much he requested, only that much he got, with the least value as 21, highest value is 30. It is his requirement. So what about this 11 to 20? So that is given by user. So what he think? Okay, so he has got a full memory, but how much he is request, only that much. Every process will get. It will not be given unnecessary extra. Okay. So now every process whichever will get created will have following contents in its space. First one is a stack, second one is a heap, third one is data and code. As you know, if you execute one of the program, you have code like C equal to A plus B, you have data A equal to 10, B equal to 20, you have some printf scanf, you might have you are using some sometimes stack whenever you are executing a factorial type of a program. Okay, see, that's what a idea. Virtual address space means what? I feel that I have got full memory. Okay. Because whatever I have requested, I got. So what I think is only I am the superior or I am the user. Okay. But there might be some other who has requested either lesser than me or equal to me or greater than me. And also whatever he has requested for him also granted. Him means other process also granted. So what other process will think? Other process will think he can use his own stack, heap, data and code. Right. So there will be some, as I mentioned here in the diagram. Okay, now it's important. Please concentrate. So as his stack operation increases, stack memory increases. Same way, heap also increases. But there is a certain stage he may not utilize full stack, full heap. Same case for second user. Same case for third user. So now what happened? There are three blocks which are non-continuous but free. I hope you understood. There are three blocks which are non-continuous but free. Can we use that space for any other work? Yes, this is called as sparse space. Okay, we can call it as sparse space. We have to remember during your Viva, something like that. Okay. So can we use, will there be possibility of if stack and heap not coincide? Okay, as a stack grows down, heap grows up, they may not contact each other. If they may not contact, that makes vacuum or empty. That empty is called as a sparse. What type of data we need to keep there? That's important. In a sparse, we should have a practice or an algorithm such that a sparse area should be loaded with the shared type of libraries. Shared type of libraries. Why and how? We will see in the one or two slides next. You can see the diagram here. I have, as I explained this, I'm from this slide of virtual address space to I'm moving here. See there now the concept is like this here. So instead of I'm showing one after another, let me show horizontally. See here, right? Hope you understood now. Okay. See, shared library of first, shared library of second. Okay. Say for example, it's a conio.h and it's a stdio.h. Just example. Generally, every program will have stdio.h. So if they exchange, what happens? Whatever this program, this process will also have own stdio.h and shared conio.h. And what about a process one? Own data conio.h, shared data stdio.h. See, they both, by sharing, they both got advantage. Less space and more utilities. They can access and work according to two header files, even though they have only one header file among themselves. This is what a diagram is. See, process one, its area, process two, its area. So one thing sure is there will be sparse space. In the sparse space, both have stored their shared libraries, so that one shared library which is present here, that is in the process one, not present in the process two. Since it is a shared, process 2 can come inside process 1 shared library and use it. Same explanation for process 2. So what is the advantage? Process 1 holding 1 using 2. Same way process another process also holding 1 using 2 because of a share. Hope you understood now. Okay, so such a space is also other virtual. So what he feel, even though he doesn't have con.io.h, still he is using. What about this? He is holding con.io, but he doesn't have stdio.h header file. So still he can use. So what is the important thing? It's a cloud virtual. You can use it without holding. Okay, so that's what. Now comes demand paging. So very simple way. Put a demand if you need. Okay, supply if it is available. Okay, if not available, say not available. If it is already there with him, inform the requesting person that already supplied. I hope it is very simple now. Okay, see, simple analysis. As I mentioned, we don't need entire program in the memory. A part of program we will take and execute. Right. So now, if page is requested, give him. Okay, condition, request is valid, page is also valid. If page is invalid, request is cancelled. That means aborted. If page is if request is valid but page is not available, means what? Bring it and supply. You will go to shop. Okay, you will request for some product. Okay, so something like some color pen, writing pen. Okay, if he knows about that pen, so and the pen is available, then he will give you. Okay, if you have already that pen, definitely you are not going to request. Okay, so third product, you are requesting for a pen which is not manufactured on this earth by any of the pen manufacturer. So what is the answer? So your request is wrong. Same point. Okay, now what type of processes should be given for the pages are where there is a IO less requirement. Why IO less requirement? Because IO means always time consuming. So we should not request for most of the IOs. But condition is what? Nowadays, who is ultimate user of the computer is a user. So we should compromise with this. Less memory required pages. Okay, why? Because already memory is shared. Okay, and we are not loading full project or full program. Part of the program is loaded. So if you load more unnecessary or more quantity of data, so program execution will become slow. So only selected part of the program should be loaded. And if we load selected part of each process, we can give space for more number of programs, corresponds to more number of users. Okay, now who will decide all this? Is MMU, Memory Management Unit, along with method called swapper. Okay, so if I show you the diagram, you can easily understand. Now you can see page A. There are two programs presently running, A and B, in the main memory. Okay, they will request 4, 5, 6, 7 pages, and pages called 18, 19, 17, 18, 19 by the request of B. Program A will request for 4, 5, 6, 7. Now, if already 4, 5, 6, 7 are there, 4, 5, 6, 7 are there already here, give him for program A. If not, okay, if not, let's say like this: 4, 5, 6, 8. So what is requested? 4, 5, 6, 7. So what we have to do? We have to swap out 8 and we have to swap in 7. Okay, by erasing not required data. So what happened here? 7 has been swapped in. So whatever a program A request, that is fulfilled. So what are the requests of program B? It's a 17, 18, 19. So what happens? 17, 18, 19. So now what is the case? Expectation and available same. So no need of swap out, no need of swap in. Okay. If it is a case, see this. Present condition I will draw like 1, 2, 3. What is the request? 17, 18, and 19. So now all the three requests are not present. So all three should be swapped out. And requested data, what are the request? 18, 19, sorry, 17, 18, 19 should be swapped in onto the memory, and so that program B will face. So you see, now you can see what program A think he has got all he is requested. What program B will think he also got all the requests. So they think that, okay, yes, I got all the requests. So let's finish the work. So they think that only they are getting a resource. Parallelly, A will also get a resource, B will also get a resource. Assume this case, program C request 80, 90, 20, sorry, something like this. 80, 81, 82. Now you check the resource, what happened here? We have up to 23. So what is its expectation? 80, 81, 82. Can we remove something and bring those which are not available? So this request is what? Aborted. Why it is aborted? We don't have resources called 81, 80, 81, 82. I hope you understood now. What do you mean by abort? That means request is cancelled, granted, and verified. Okay, so let me show you 3 point. If request is present, possible, give it. If the request itself is wrong, abort it. If request is correct and data is not available, then bring the data and provide the request. So whoever deals with this exchanging of a pages is called as pager. Okay. So now, what are some possibilities, some concepts related to paging method? So whenever we are swap out, swapping pages corresponding to the frames, we should able to predict. Predict means guess which process or page may, sorry, which process may request for which type of page or which type of frames. If we are sure, okay, this process may request this page, then we can bring it little early. Okay, so if you bring it little early, definitely performance increases. Okay, now same algorithm. Who will do this memory management unit will implement this concept. If pages required are already present, do not make any changes. Okay, as I told here in the diagram. So what is its requirement? Let's say 17, 18, 19 is a requirement. So what is existing? Existing is also same, 17, 18, 19. Check, compare both are matching, so no change. Okay, I hope you understood now. No change. See, no difference in the requirement and availability, so we can provide the service. Okay, next, small change. Here is 20 is available, 19 is required. So is requirement is wrong? No, it is correct, but we don't have. So it is option that time, bring it from the memory and give it to the user. See, we brought it from the memory, give it to the user. But if it is 81, 82, 83, so the resources are not available with us, so we can avoid such a type of request. Pallavi. Pallavi, please mute. Okay. So now, basic concepts, as I told, that's a main part. So if your expectation is the same as the present situation, no changes. Okay. If the request is not present, so we have to change. Okay, how to change? Based upon the priority, we can change, as I told. Okay, now coming for the next one more important, here is a diagram, right? Whether how to decide request is valid and request is invalid. So there will be data structure in the page table, as I told in the last hashed page table concept and inverted hash page table concept. So which frame, which page, and also we can hold attached data structure called valid and invalid. So now condition, valid, invalid, we will attach. Now very important, and try to remember this point. Valid means request is valid, and it is present. So just now I have explained, no, 17, 18, 19 you have requested. I mean process has requested. 17, 18, 19 are there in the memory. So that is called as valid. The word we use is memory resident. Now there is a bit called I. There is a bit called I. I means invalid. Please don't assume this as it is requesting for 80, 81, 82, which is results to a abort. That's not a case. Present thing is request is 17, 18, 19. Present thing is 17, 18, 20. What is the case then? If 17, 18, 19 are requested, 17, 18, 20 is present. So what we will do? We will take out 19. We will place, we will take out to 20. We will place 19 so that request and available we will match. Just now I have told same way. So this I don't assume abort case, assume replacement case. Okay. And second, initially all bits are I. Okay. Can anybody give the answer in I? I bit means here I will type. It's not the abort example. Instead, it's a not available. So please check in the chat box. I told not the case of abort, but it's a case of not available. Abort means totally not possible to provide, but not available means we can provide the service by exchanging something. Okay. So who will do all this work? Again, it's a memory management unit. Okay. So I will show you the diagram. Hope you will understand now. So once we explain this, it is easily possible. So logical memory is this much, physical memory is this much, and this is what a disk. Okay, page table. Now you can see here. So these all are the pages loaded here with the frames. Page 0 to page 7 are loaded onto frame 4, 6, and 9. What frame 4 will have 0th page? What is the name of 0th page? A. You can see as right. Okay. So 6th frame will have page 2. Correct? So 6th frame will have page 2 content. What is that? C. You can see here. 6th frame, page 2 content. 9th frame, page 5 content. 9th frame, page 5 content is what? F. I hope you understood. This is how the mapping is done. So why it is valid and remaining are invalid? Valid because right now they are present in the physical memory. Okay. Invalid, remaining are not present in the physical memory, or okay, this frame wise. Hope you understood now. Okay. So this page table, and even though we have DE, in the disk, why they are not in the physical memory is for the D page 3. Page 3, what is a bit? It's an invalid. So that means what? It is not available in the memory. For the H, what's the page 7? What is 7 bit? It's an invalid. Hence, don't load on the physical memory. I hope you understood now. For whom it's a valid, only those will get a location on the physical memory. Okay. So less than a minute is remaining. Please give your attendance in the chat box. I will try to continue. Okay. Okay. This I will not start.